Hello, my name is Andrew Kolarits, and welcome to my presentation on my reproduction of the paper titled Representing Visual Classification as a Linear Combination of Words. So to go through a quick agenda of what we're going to be talking about, first we're going to talk about the general problem, and then we're going to talk about the specific approach of the paper specifically, talk a little bit about my attempt at reproducing the paper, go into the results of my reproduction and comparing it to the original paper, and then talk about the extension that I created. So what is the problem that the paper is trying to address? Well, modern vision models are able to achieve high levels of accuracy, but often struggle in showing end users why they are making the predictions that they are making. Current models often rely on non-human readable features, dataset biases, and a lot of black box decision pathways. However, in real-world settings such as healthcare or security industries, models need to be able to explain why a certain classification was predicted. So the question we're trying to address is how can we represent a model's vision decision in clear, natural language without sacrificing performance? The specific approach of the paper used the SIM-ISIC dataset, which is a collection of dermoscopic skin lesion images with labels for melanoma detection. Each image is labeled as benign or malignant, and the paper uses OpenAI's CLIP, which is a contrastive language image pre-training system to embed each training image along with CLIP's 49,000 token library. So the token library is used to describe each image and why it was given its certain classification. It then trains a linear classifier on the image embeddings to predict vocabulary labels for each image, and then fits a linear regression from the text embedding space to the classifier weights. And this expresses the classifier as a weighted sum of word vectors. And then the learned coefficients for each word become a human readable explanation on what the classifier relied on exactly to make the prediction that it made. Getting into my reproduction, I first had to do some data pre-processing. The original paper originally used two different data sets. However, one was unable to be downloaded. You had to have certain privileges and be part of a certain community to have access to it. So I only used the SIM-ISIC dataset, which was publicly available. However, in this data set, the test data that was in the data set did not have any kind of labels of being benign or malignant. So I followed the paper in which they took the training data from the SIM-ISIC dataset and broke it down into 80%, 20% for training and test data. The paper also had to revise the data set to have a 2-to-1 ratio of benign to malignant pictures. That's because the original data set had like a 48-to-1 ratio of benign to malignant, so the model was simply predicting everything to be benign and getting a 98% accuracy. So this ratio of 2-to-1 stopped that bias from occurring. Looking at my results after my reproduction, I was able to achieve a very similar accuracy and ORIC, which is area under the receiver operating curve. And this ORIC measures how well a model was able to separate the two classes, those being benign and malignant. One being a well separation between the two classes, and 0 meaning there's no separation between the two classes. It's just predicting benign the entire time. So the original paper had an accuracy of 76.5. My reproduction ended up having an accuracy of 73.9, and an ORIC score of the original paper being .813 and mine having .825. So very similar results in terms of accuracy. On the right here, you can see the weights of the assigned descriptive words. You can see that my reproduction had similar weights in regards of if a word had a positive weight, mine also had a positive weight, but if it had a negative weight, mine also had a negative weight. However, there were differences between like my high contrast. The weight given to high contrast is much higher than what the original paper gave to high contrast. And I attributed this difference to my reproduction having different training and test data. Yes, both training and test data sets came from the overall sim ISIC data set. However, the 20% that I chose to be the test data is probably different than what the paper chose to be their 20% test data. So I think that difference in data set sampling is what produced the variance between the weights. Going into the extension that I chose to implement onto this paper, I chose to implement something called vocabulary pruning. And I like to talk about the motivation and the method before going on to the results. So the original paper used CLIP, which has a token vocabulary of roughly 49,000 tokens. And this size of the text vocabulary has a direct impact on both the computational cost and the quality of the outcome of the model. But this large vocabulary probably contains many words that are just noise, redundant, or irrelevant to the problem space that we're talking about. So what I attempted to do was use a large language model, specifically ChatGPT, to generate a smaller, more relevant word vocabulary of roughly 1,900 words instead of CLIP's 49,000. I then tested this vocabulary size ranging from just 10 words all the way up to 1,900 words. Looking at my results, a smaller, more relevant vocabulary was able to achieve similar results to the large CLIP vocabulary at roughly 1,000 tokens. So as you can see in the graph, when my vocabulary size is really low, 0 all the way up to roughly 1,000, and then at 1,000 there's a big spike. Some key point right here where it jumps all the way up to be above 80% accuracy, or all the way up to almost 75% accuracy, which is extremely similar to what the original CLIP vocabulary was getting at. So with this much smaller vocabulary, I was able to achieve very similar results to the original CLIP dataset while having much improvements in speed of computation and the overall size of the model. Thank you for listening to my presentation on my report of the paper.